In this lesson, we'll talk about graphs of basic polynomials. We're going to look at different degree polynomials, starting from the 0-degree polynomial, which is a constant function. Using a table of values, we need to graph each function and observe their properties, such as domain, range, and the general shape. Our first example is f of x equals 2. Normally, if we don't really know how the graph of a function looks like, we may want to use a table of values, such that the left column will contain the input x, and the right column will be the value of the function for this particular input. Since this function is really simple, there's not much calculation here, so we can fill up this table really quickly. The x value could be, for example, -1, or 0, or 1, or 2. And since the function is actually constant, it does not really depend on x. X can be anything, and the value of this function is constantly equal to 2, so there's no calculations at all. Here are our points. Let's plot them. In all of the graphs, I will assume that 1 square represents 1 unit. So point -1, 2 is here, 0, 2 over there, 1, 2, 2, 2. And we already see a pattern. Any other input x, for example 3.5, will result in a value 2 as well. So we can graph this function. That's a horizontal line coming through the point 2 on the y-axis, representing this constant function. Basically, any constant function will have a graph of a horizontal line. What is the domain of our function? Well, if we project this horizontal line onto the x-axis, every single number is shadowed. That means we could take any real number for the input, because the output doesn't even depend on the input. So the domain is all real numbers. What about the range? Well, as you remember, the range is the projection of our graph onto the y-axis, or the set of all possible values that the function assumes. But in this case, the only value that is assumed is 2. There is no other values. So the range here is the set composed of one element 2. Our second example is a function that is called identity. That's f of x equals x. Why identity? Because if we have an input x, the output is exactly the same. There is no change. So we can fill up the table. Again, let's try to take some negative numbers and some positive numbers. So -1, 0, 1, 2. Serve perfectly well here, and the value is exactly the same. So if input is -1, the output is also -1. If input is 0, the output is 0. If input is 1, the output is the same, and for 2 is the same too. So let's plot those points. Again, that's -1, that's 1. So -1, -1, that's the point. 0, 0, here it is. 1, 1 over there, and 2, 2 over here. So we can predict how the graph may look like. It will be a diagonal line. Let's graph it. Here it is. And domain and range. Again, for domain, there's no problem. We can take any real number, and we can see it by projecting our graph onto the x-axis. Every single real number will be shadowed. That's our domain. So let's record this. Domain is all real numbers. What about range? Well, range is the same. If we shadow the graph onto the y-axis, every single value on the y-axis will be taken. The range is all real numbers as well. So let's write it down, all real numbers here. And let's clean up our extra shadings, just because I want you to remember the shape of the function. So, constant function, horizontal line, identity function, diagonal line. Okay, let's see another example of a line. We have first degree polynomial, which represents a linear function, 2x minus 1. We already know how to graph linear functions using various methods. However, let's fill up this table of values. So again, let's take numbers like -1, 0, 1, and 2. Obviously, we could take some other numbers, but those are good numbers to take. They are easy to calculate and cover both cases, negative and positive. Okay, so if we put the input x equals -1, the output is 2 times -1 minus 1, which altogether is -2 minus 1, so it's -3. So the point -1, -3 belongs to the graph. -1 and -3 is here. That's our point. If we plug in 0 for x, then 2 times 0 minus 1, oh, that's -1. If we plug in 1, it will be 2 times 1, which is 2, minus 1, so it's 1. And finally, if we plug in 2, it will be 2 times 2 minus 1, which is 4 minus 1, so it's 3. Okay, let's plot those points. 0, -1 is here, 1, 1 is over there, and 2, 3, that's our 2, that's our 3, is here. It looks like those points are collinear, so we didn't make any mistake. Let's graph it. Here it's our function. Similarly as before, if we project this graph onto the x-axis, everything will be covered. That means the domain of any linear function is all real numbers. What about the range? As long as the graph is slanted like this, the range will be all real numbers as well. The only exception would be if we deal with a horizontal line, like in example A. Let's see the next example. Well, this time we go one step higher to the second degree polynomial, x squared. So we need to know the shape of this basic quadratic function, which is called parabola. How does it look like? Well, again, let's check a couple points below 0 and above 0. Maybe this time start from -2 and then -1, then 0, 1, and 2. Since we are squaring those numbers, that's really easy to get the values. -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. We can already notice some properties of this function just by looking at this column. I'm sure you can observe that the 0 is a single one, and then starting from the 0, one step apart, we have exactly the same values. And going 2 steps apart, we have again the same values. So those values are distributed symmetrically. The central point 0, 0 will be called vertex. Let's plot those points. -2, 4 is here. -1, 1 over there. Then 0, 0, 1, 1 here, and 2, 4 again over there. So we need to connect these points. But this time we are not using any ruler because parabola has no linear parts. What we need to do is nice and smoothly connect those points just by hand. Okay? That's how the shape should look like. Make sure that when you draw it, you round the vertex. Don't make a pointy vertex like this. So please don't try to use a ruler here. Okay, let's look again at the distribution of those points. Try to remember this pattern because it may be useful in graphing parabolas in other situations. We may start with the vertex, and then what we do, we go across 1 and 1 up on both sides, and then across 2 and 4 up on both sides. So 1 across 1 up, 2 across 4 up, because 2 squared is 4. So those are the easiest points to get for parabola. Okay, now let's check the domain. Domain consists of all those points that will be shadowed by the graph. If I project it onto the x-axis, everything will be covered on the x-axis. That means domain consists of all real numbers. It's good to realize that this curve doesn't stop here. It's just our graph paper ends. But the curve proceeds, so sooner or later all the x values will be shadowed. Therefore our domain is all real numbers. What about the range? Well, remember we check the range by looking at y values. Since we are squaring everything, we will never get negative numbers. And as you see, the graph doesn't appear below x-axis. Everything is above x-axis. So when you project the graph onto the y-axis, everything is covered but starting from 0 up, nothing below 0. Therefore, the range of this function is the interval from 0 to infinity. 0 is included because that's the value of the vertex. So far we know that a graph of a constant polynomial is a horizontal line. A graph of a first-degree polynomial is represented by a line, and a graph of a second-degree polynomial is some sort of parabola. This is another parabola. The only difference between the previous example and this one is the minus in front of x squared. So let's see how this quadratic function will behave. Again, we'll start investigating numbers like -2, -1, 0, 1, and 2. Let's take those inputs, plug into the formula. We'll have negative bracket -2 square. So it's negative, and whatever's in the bracket square, it's 4, so it's -4. Similarly, -1, when we square it, it becomes 1, but then we have extra negative. So altogether is -1. 0 when squared is still 0, and -0 is also 0, so that's nothing to calculate here. And with positive numbers it's even easier, so it's -1 squared, so it's -1, and -2 squared, so it's -4. As we expected, we have symmetry around the 0. The values to the right or to the left of 0 are exactly the same. Okay, let's plot those points. -2, -4. That's our point. -1, -1, so it's here. 0, 0, 1, -1, and 2, -4. Oh, that looks like a parabola, but upside down parabola when we connect those points. Let's do it. Here's our upside down parabola. So what's the domain of this shape? If we project all the values onto the x-axis, you can imagine that the entire x-axis will be covered. So domain for any parabola is indeed all real numbers. Basically, domain of any polynomial is all real numbers, so we don't have a problem here. However, the range can be different for different polynomials. So for example, in this case, if we project our graph onto the y-axis, everything will be shadowed, but below 0. So the range is from -infinity until 0. Interval from -infinity to 0, including 0. That's our range. Now, let's look for a second how this graph relates to the basic parabola. Here's the basic parabola. So how can we obtain the green graph from the orange graph? Well, if we flip the orange graph over the x-axis, we will get exactly the green graph. So the transformation of the basic parabola needed to obtain the graph of -x squared is symmetry in x-axis. Sometimes, instead of writing this phrase, symmetry in x-axis, we may use a shorter sign, capital S with subindex x. That stands for symmetry in x-axis. Okay, let's try another example. Again, some sort of modification of basic parabola, x squared, but it is -4. One more time, quadratic function. Let's choose the same inputs for x, -2, -1, 0, 1, and 2. And then we need to calculate the value of this function. -2 squared is 4, and then -4, that makes it 0. -1 squared is 1, and then -4, it makes it -3. 0 squared is 0, -4 is -4. 1 squared is 1, -4 gives me -3. As you see, we have the symmetry. So what to expect next? Even without any calculation, I know it will be 0. But let's confirm. 2 squared is 4, -4, yes, it is 0. Okay, let's plot those points. -2, 0 is here, -1, -3 is over there, 0, -4, and then 1, -3 is here, and 2, 0 is over there. So let's connect those points. Here's our shape. Again, it looks like a regular parabola. However, the vertex is not at 0, but at -4. If I want to see clearly the domain, let's extend those branches a bit. We already know that the domain of any polynomial is all real numbers. Therefore, domain of this particular function will also have to be all real numbers. But let's see it one more time on the graph. If we project this graph onto the x-axis, those points will be covered and they go forever there. And these will be covered. And those will be covered. That means everything is covered. Yes, indeed, our domain is all real numbers. So now to see the range, let's project all the points onto the y-axis. What will be covered? Everything starting from -4, nothing below -4. So from -4 till infinity. Let's record this from -4, including -4, because that's the value for the vertex, up to infinity. Here's our range. Let's erase the shadow to see nice and clearly our parabola. Now, how can we compare the green graph with the graph of x squared? Let's recall the graph of x squared. That was like this, with the vertexes 0, 0, 1 across 1 up, 2 across 4 up. If we slide this graph 4 steps down, it will exactly match our shape. And this is what we should expect, because when you analyze the formula, we started with x squared, and then we subtracted 4 from all values of the regular x squared. So again, that was a translation down by 4 steps. Okay, therefore the transformation of basic shape that was applied to obtain the green shape is translation by 4 steps down. Sometimes I like to use a shorter notation for this kind of transformations. Capital T for translation, and to indicate in which direction, I like to use vector notation as a subindex here that describes the direction of a general point. So let's say if we had a vertex here of the basic parabola, this vertex went down by 4 steps. That means it followed that vector. That vector has coordinates 0 because we are not moving horizontally, and the first coordinate describes the horizontal movement. So 0 horizontally and 4 steps down, so the second number is -4. Generally, maybe on the side, a vector that goes, for example, like this, A steps forward and B steps up, has coordinates A, B. That's what this notation stands for. But if you don't like this notation, you're more than welcome just to describe the movement by words. Next, another quadratic function, but it's a different modification of our regular x squared. This time, instead of x, we have x minus 2. So we're changing the input somehow. Let's see how the graph of this function may look like. Again, we need to fill up the table of values. Let's pick some numbers for x. But this time, you will see that the important point, the central point, is actually 2, not 0. So let's try a couple numbers below 2 and above 2. Okay, let's start with point like 0, 1, 2 as a center, and then 3 and 4. You will see in a second why. Okay, let's plug in 0 to our formula. So we have 0 minus 2, so it's -2 squared, which is 4. If I plug in 1, I have 1 minus 2, which is -1 squared. That gives me 1. Plug in 2. Oh, that's why 2 is so important, because 2 minus 2 is 0. So that will serve as our vertex, like 0, 0 in the basic shape. So let's try 3. 3 minus 2 is 1. 1 squared is 1. And 4 minus 2 is 2. 2 squared is 4. As you see, again, we have this symmetry. So how did I know that the x value 2 will be the central one? Well, because normally this whole bracket would have to be 0. But this whole expression x minus 2 is 0 when x is equal to 2. So the 2 has a special role here. Okay, let's plot those points. 0, 4 is here. 1, 1 over there. 2, 0 here. 3, 1 and 4, 4 again. Here we go. We see that the parabola is shifted. It's not at the center. It is going to the right. Okay, let's graph it. Here it is. Again, you can check by yourself. The domain of this parabola is all real numbers. What is the range? Well, if we project all the points of the graph onto the y-axis, all the points will be covered from 0 to infinity. So from 0 to infinity. That's our range. Okay, and now again, let's try to describe the transformation of the basic shape, basic parabola, in order to obtain this particular parabola. Here's our basic shape. What do we need to do? Well, we need to move it to the right by 2 steps. Here's how it looks like. They match each other. Okay, so the transformation is again translation, but this time horizontal translation. Remember, before it was vertical translation, now it's horizontal. So translation by 2 steps to the right. Or we can use a shorter notation by using capital T for translation and describe the coordinates of the vector. So this time we have horizontal movement, therefore the first coordinate will be 2, and no vertical movement, therefore second coordinate is 0. I use those pointy brackets to distinguish between coordinates of a vector in opposed to coordinates of a point or even interval. Okay, so I guess we have enough examples of quadratic function. Now let's go 1 degree higher. We're going to look at cubic functions. How the basic cubic function, which is third power of x, looks like. Let's fill up the table of values first. So let's choose some numbers that are to the right of 0 and to the left of 0. We can't use two large numbers because when we cube them, they grow really quickly. Okay, let's try 0 as a center, obviously -1 and 1, and maybe -2 and 2. So -2 cube, it's -8. -1 cube is -1, 0 cube is 0, 1 cube is 1, and 2 cube is 8. Okay, we'll try to plot those points, even though 8 goes a little bit out of our grid, but we'll estimate. I'm going to start with the central point, the 0, 0. Here it is. Notice that we have some sort of symmetry here, but not quite the same as in parabola. We have exactly opposite numbers at the same distances from 0. So 1 to the right and the value is 1, 1 to the left and the value is -1, here and there. So far, if we just look at these 3 points, it looks like they are collinear. However, don't be misled by it. This is not a line, it's a cubic function, it must be a curve. So don't even think about using a ruler here. Let's finish our points. 2, 8. 2 is here and 8, since this is 5, 6, 7, 8, approximately here. Similarly, -2, -8. So it's -5, 6, 7, approximately here. Now we need to connect all those points nice and smoothly. If we are not quite sure what's going on around 0, we can check a couple more points. For example, 1/2. If we take 1/2 and cube it, we end up with 1/8. So, for a number 1/2, the value will be very, very close to the x-axis, somewhere here. Similarly, for a number -1/2, the value will be -1/8. So again, it's very close to the x-axis. Therefore, as you notice, the shape will be flattened around 0 and then grows really fast to the right and diminish to the left. Okay, let's join those points. We have a shape of a snake. As usual, the domain of any polynomial is real numbers, so it is real numbers here as well. And this time, if we look at the values of this function, that means project the graph onto the y-axis, every single point on the y-axis will be taken. That means the range is all real numbers as well. All real numbers. Okay, so that's the shape of a cubic function. And the last function, it's a modification of the basic cubic function x cubed. What we did here, we added 1. So maybe you already predict how the graph will look like, but let's check it. Again, let's take numbers like -2, -1, 0, 1, and 2. When we cube -2, that will be -8, but plus 1, it becomes -7. -1 cube is -1 plus 1, that becomes 0. 0 plus 1 is 1. 1 cube is 1 plus 1, so it's 2. And 2 cube is 8 plus 1, that will be 9. Okay, let's plot the numbers that we can. We probably won't be able to plot 9, but let's see what will happen. -2, -7. So since this is -5, -6 is about here, and 7 about here. That's our point. negative 1, 0, oh, it's already here, so it grows really fast. Then 0, 1 over there, that will be our central point. 1, 2, and 2, 9. So at 2, we'll have to go 9 steps, so even a bit farther than our screen. We're not going to plot this point because it's too far, but we keep in mind that the point is somewhere here. So the shape will look somehow like this with the center exactly here. Let's connect those points. Here's our snake. Similarly as before, you can see that the domain is all real numbers and the range is also all real numbers. So there's no problem with range for cubic function. And again, if we want to see the transformation of the basic shape, here's our basic shape in yellow, then as we can predict, since we are adding 1, this whole graph of the x cube will have to be moved one step up to match the graph of x cube plus 1. Let's see the movement. Here it is. Okay, so the transformation of basic shape is the translation by one step up. In shorter notation, it will be capital T for translation, and the vector from here to there. There is no horizontal movement, so the first coordinate of this vector is 0, and the vertical movement is one step up, so the vector is 0, 1. Translation by the vector 0, 1. Okay, those are all examples that I have for you for now.